In the previous lecture, we discussed three laws of motion and reviewed some basic aspects of vector algebra. We are now going to apply this understand equilibrium of bodies in the statics, the part when we say the body E is in equilibrium. What we means that body is not moving at all, even and though there are maybe some force acting on it. In general, equilibrium means that there is no acceleration in the bodies is moving with constant velocity. But in the special case, as we take this constant to be zero. Let us start by observing what all can a force us do to a body. On one obvious thing, it does not an accelerate does us it does to accelerate it at our body. So if we take a point and particles P and apply a force on it, it will accelerate it. Thus, if we want an acceleration to be zero, the sum of all force applied on it must be vanish. This is condition for equilibrium um, of point particles. So far are point particles in the equilibrium condition, and then summation of all force S is zero, where summation and is Fi, where Fi I is the integer, or we can write it 1 2 3 are the forces on applied on a point particles. Else that is the 3 there is in equilibrium of point particle. But in engineering problem we deal not with point particles but with extant object. An example of a beam holding a load with it shown in figure. The beam is in equilibrium under on weight at W and the load is the force support S1 and an S2 apply on it. To consider an equilibrium of such extant bodies, we need to see the other effects of that force as produced on them in these bodies is in addition to providing acceleration and of these bodies, an applied force has two more effects. One, it tends to rotate the body, and two, it deforms the body. Thus, a beam put on two supports S1 and S2 tend to rotate clockwise as about S2 when a force F applied downward. And in figure here you can see in figure, a beam of supported S1 and S2 tends to rotate clockwise under the force F. The strength and or ability of a force to rotate the body about a point O is given by torque generated by it. The torque is defined as the vector product of displacement and vector r0 from 0 to the point where force is applied. Thus torque is r0 into F. This is also known as the moment of the force. Thus in figure above, the torque about S2 will be given as the distance from the support time. The force and its direction will be E into the plane n of the paper. Here, from the way that torque is defined, that torque with given direction tends to rotate the body on which it applied and perpendicular to the direction of torque. Further, the direction of rotation is obtained to by lying the thumb, one right hand, and in the direction of torque. The finger that shows us in this the way of bodies tends to rotate. Notice that the torque due to force will vanish if the force F is parallel to R. We now make a suitable point and about the tendency of a force to rotate a body. It is that even if a net force applied on a body is zero, the torque generated by them may be vanished as the force will not give any acceleration to the body, but it would tend to rotate it. For example, if we apply equal and opposite force to ends of the rod, as shown in figure, the net force is zero. It will still tendency to rotate it. So the considered equilibrium bodies is we not only have to make sure that the net force is zero, but can also or that the net torque is also zero. The third possibility of this action by force, which have ignored above, which is highly expected in the case of mass on the top of the spring, is that the force is deforms body. Thus, as in the case of being under a force, the beam will may deform the various way. It may compressed, it may get elongated, may bend, and a load on the top of the spring is obviously deformed the large amount. And in the first case, we assume the deformation is small and therefore negligible. We assume that internal force are so strong that just that there is no deformation by the applied external force. This is known as treating a body as a rigid body. In this course, we are going to assume that all bodies are rigid. So, the third kind of action is not considered at all. So we now focus the state equilibrium of rigid bodies. Yes, as started, we are going to assume that external forces are so great that the body does not deform. The only condition for equilibrium them are the body should be accelerated and should not be moved as discussed earlier as ensured. Is summation of Fi equals to 0. That is assumed that accelerating force acting must be 0. No matter what point on the bodies are applied. For example, we consider the figure applied by it. The bodies, for example, the beam and the figures let the applied by the support S1 and S2, F1 and F2 respectively. Then the equilibrium N is in required that. Then F1 plus F2 plus W plus load out equals to 0. Assume the direction towards the top of the page is y direction, and then translated F1j F2j plus F2j minus Wj minus Lj equals to 0, or F1 plus F2 minus W minus L बराबर 0. The condition is sufficient to make sure that net force of this rod is 0, but as we learned earlier, Also, the every experience tells us that even a zero net force can rise a turning on a road. So F1 and S2 must be applied in such a point that the net torque on the beam is also zero. This is given below in the second rule of equilibrium. Simulation of movement of force is supported at a point and 0. Therefore, summation of torque I0 equals to 0, where torque I0 is the torque due to force Fi about a point O. Uh, Once the may ask the point summation torque I equals to 0 should be taken about to many different points, or it's sufficient to about to consequent point. The answer of that any covariant point sufficient because the condition about the specifies the net on the body is 0. Then the torque as the independent of a point about to which it is taken. We will prove it later. Thus the two conditions are both necessary as sufficient and for equilibrium. That is all we needed to do achieve equilibrium. So in the principle solving the equilibrium is quite easy, and what we should learn how to apply this condition efficient in the different engineer situation. We are therefore going to spend more times on these topics individually.